Every time you look at a modern electric vehicle, you're looking at a brilliant piece of engineering with a massive, heavy secret. Hidden beneath the floor is a battery pack that can weigh over 1,000 pounds, and for the most part, that weight does absolutely nothing to help the car stay rigid. In engineering, we call this parasitic mass. It's weight that provides energy but doesn't contribute to the vehicle's structural integrity. It's like carrying a heavy backpack full of fuel. The fuel helps you move, but the backpack itself is just an extra burden your muscles have to fight against. But what if we can make the backpack part of the runner's own skeleton? That is the promise of Structural Battery Composites, or SBCs. It's a technology that turns the very frame of a car, a plane, or even your phone into its own power source, eliminating the need for a separate battery pack entirely. To build a structural battery, we have to rethink the very chemistry of a battery cell. In a standard lithium-ion battery, the electrodes are thin foils coated in paste. They have zero structural strength. In an SBC, the carbon fiber is the structure and the electrode at the same time. The carbon fiber used here is specifically chosen for its high tensile modulus, meaning it doesn't stretch easily. At the same time, its atomic structure is layered, which allows lithium ions to tuck themselves neatly between the sheets of carbon atoms during charging. This process is called intercalation. This dual-purpose design is the key to everything. By using the same material for two different jobs, we eliminate the dead components like the heavy copper and aluminum current collectors found in traditional batteries. It's a masterpiece of efficiency. But the real engineering hurdle is the electrolyte. In your phone's battery, the electrolyte is a liquid, but you can't build a car frame out of liquid. You need a solid that can act as a glue to hold the carbon fiber layers together while still allowing ions to zip through it. Engineers use a special polymer-based electrolyte. Think of it like a dense sponge. It's solid enough to resist bending and crushing, but on a molecular level, it has tiny pathways that allow lithium ions to travel from the anode to the cathode. It's a solid-state revolution happening inside a composite material. This polymer must also be an electrical insulator. If it allowed electrons to pass through, the battery would short-circuit instantly. It has to be a very specific type of gatekeeper. Yes to ions, no to electrons. Getting this chemistry right is one of the hardest problems in materials science. Now, let's talk about the cathode side of the sandwich. Since carbon fiber by itself isn't a great cathode material, engineers have to coat it. They use a process called electrophoretic deposition to apply a thin layer of lithium iron phosphate onto the carbon fibers. This coating is only a few micrometers thick, much thinner than a human hair. This ensures that the fiber remains flexible and strong during the manufacturing process. Once coated, these fibers are woven into a fabric, just like the carbon fiber used in Formula One cars or high-end bicycles. The result is a power fabric. It's a material that can be molded into any shape, a car door, a wing spar, or a phone chassis, and it will store energy throughout its entire volume. This is the definition of making the invisible visible. The power is hidden inside the very walls of the object. But there's a catch. When you charge and discharge a battery, the materials actually expand and contract. In a normal battery, this isn't a huge deal because the casing is flexible. But in a structural battery, that expansion could cause the car's frame to crack or delaminate over time. Engineers solve this by using nanostructured materials that can absorb those tiny movements without breaking the bond between the layers. It's like building a skyscraper with dampers that allow it to sway in the wind, except here, the wind is the flow of lithium ions. This is why the energy density of structural batteries is currently lower than traditional ones. We have to give up some space for the structural part of the equation. However, because we're saving so much weight on the rest of the car, the total efficiency can still be much higher. So how much energy are we talking about? Current prototypes can store about 25 to 30 watt-hours per kilogram. That's significantly less than a Tesla cell, which is around 250. But remember, the Tesla cell is dead weight. The structural battery is the car's actual body. If you replace the entire steel frame of a car with this material, you don't need a 250 watt-hour battery. You can achieve the same range with a much lower energy density because the car itself is hundreds of pounds lighter. It's a radical new new way to do the math of motion. And the best part? This technology is getting better every year. Researchers are already aiming for 75 watt-hours per kilogram, which would make structural batteries competitive for almost every type of transport. We are on the verge of a world where the battery is no longer a part of the machine, it is the machine. As amazing as structural batteries are, they introduce a terrifying new problem: safety. In a traditional car, the battery is protected by a crumple zone, but in an SBC car, the battery is the crumple zone. If you get into a crash, you are literally crushing your energy source. When carbon fiber breaks, it can create sharp, conductive shards. If these shards pierce the electrolyte layer, they could cause a massive short circuit. Because the battery is spread throughout the whole car, a small dent in the door could theoretically start a fire that involves the entire chassis. To solve this, engineers are designing modular chassis. Instead of one giant battery, the frame is divided into hundreds of isolated cells or zones. If one zone is damaged, a smart management system instantly disconnects it from the rest of the car, keeping the energy contained and the passenger safe.